RNase contains many amino acid residues, dictating its geometry and specific binding of substrates. The proximity and chemical properties of the residues help determine which bonds are broken and formed in the substrate, leading to the formation of more specific products. In addition, the active site of this RNase enzyme contains a pyrimidine binding site, which specifically binds an RNA substrate with a pyrimidine base, and cannot accommodate an RNA substrate with a purine base. In the active site of RNase, histidine 12 acts as a base and deprotonates the 2' hydroxyl group of a pyrimidine nucleotide residue. The resulting nucleophilic oxygen atom attacks the central phosphorus atom. After a few rearrangements, the resultant negatively charged oxygen atom in the high-energy intermediate is further stabilized by the positively charged lysine 41 in its close proximity by ionic interaction. Histidine 119 donates a proton to the 5' oxygen atom of the downstream nucleotide residue to complete the production of an alcohol leaving group as the RNA molecule is split. The downstream RNA fragment leaves the active site as a first product. A 2'/3' cyclic nucleoside monophosphate is left in the active site, and now water can enter the active site. Histidine 119 acts as a base and deprotonates a water molecule, and the resulting hydroxide nucleophile attacks the phosphorus atom. Once again, following rearrangements, the negative charge developed on the oxygen in the high-energy intermediate is stabilized by ionic interaction with the positively charged lysine 41. To revert to a more stable electron pair configuration with 4 ligands around the central phosphorus atom, its bond to either the 2' or 3' oxygen atom must be broken. If the bond between the phosphorus atom and the 3' oxygen atom breaks, the 3' oxygen will carry a negative charge. The imidazolium form of histidine 119 is not geometrically positioned to donate a proton to the 3' oxygen atom. Therefore, this process is not as favorable. In contrast, the favorable geometric proximity of histidine 12 allows it to donate a proton to the 2' oxygen atom, creating a better leaving group. The specific geometry favors breaking the 2' oxygen bond. Therefore, only 3' phosphate products are formed. Thus, the bond between the phosphorus atom and the 2' oxygen atom breaks, resulting in a 3' nucleoside monophosphate. After the product leaves the active site, the enzyme has been recycled back to its original state and is ready to catalyze again.